Hi everybody. We're going to do a quick little random video today. It's been kind of busy at work, but I thought I'd get this out here. A couple things I want to mention. Number one, I'm putting on my idiot boots. So, if you recall, when we did the 2285 Marantz, I was a bit concerned about the tops of these capacitors being exposed to someone touching them. And I have to say, I stand corrected. Mark, one of my friends there online that every once in a while gives me a gentle nudge in the right direction if I'm going the wrong way in the comments section, mentioned that he has measured these in the past, and in fact there is no electrical connection between the case of the capacitor and the capacitor itself. So I went ahead and I measured with an ohm meter from both pins to the case, and sure enough, there is no electrical connection on these. So even though they're metal, they don't connect to either of the elements of the capacitor. Now, anytime you're looking at these axial capacitors like this Mallory, this is an older cap, it in fact does have the case connected to one of the leads, the negative terminal. But any of these big capacitors, like these snap fit ones, all these modern new ones, they do not have any electrical connection to either lead. And even this one, you would think, because it's insulated with this little cover on the top, I actually took the meter probe and I measured underneath this shrink wrap to the actual metal case. Sure enough, it doesn't even have any electrical connection. I then went to the original can capacitors. Notice they're all sealed up as well. And I went from all of the terminals to the case underneath the shrink wrap again on this, and even it doesn't have electrical connection to anything. I was quite surprised by all that because, you know, the older can capacitors, especially the ones you see in the old tube gear and everything, those we know for a fact use the outside can as a conductor. And even the ones, I'm looking down at that an old receiver down there, the ones that have the cardboard covered capacitors that are on the little fiber washers that are isolated, those in fact do have the can connected to one of the elements, which is why they have that cardboard over top of them and why they're on that little fiber, Bakelite, whatever it is, oval wafer to isolate it from the chassis. So these newer capacitors, no longer a need to worry about it. And I even checked all of the small caps like the Nichicons and stuff that I have. None of them have the connection either. So I got us all worked up for nothing. So I thought I would come out immediately and let you all know that I stand corrected. That's good news because we really don't have to worry then about covering these on that 2285. And neither do any of you. Okay, another thing, I got a lot of good comments about some of the work that I did on the 2285 when we were tracing through some of the problems that we found on there, and especially when we were using the HP 3580A spectrum analyzer. And a lot of you had a lot of good comments and a lot of good questions. So the first thing I want to get into is mention that we were looking at, when we were troubleshooting that problem with using the ceramic capacitor, and I replaced it with the electrolytic, which I still to this day, I have no clue why that happened. And I half believe that, well, I almost fully believe that if I took those Nichicon Golds out of there and I replaced them with the original, these little film capacitors, I don't think we would notice any difference. And I don't know if maybe we would still see that distortion. I don't know. I'm just going over in my mind, what the heck could that have been? I mean, I don't think it was noise in the probe or not making a good connection, because both channels were exhibiting the same issue, and both channels removing those ceramic or these little film capacitors And replacing these film capacitors with those electrolytics made the problem go away. Now, it begs the question, on many of the amplifiers, go back through some of my videos, like the old Pioneer SX, 1050, the 1980, all the Pioneer things, the other Marantz we did, the Sansuis, all of them, one thing in common that I noticed was when you get onto like the tone control board or the preamp boards, the boards contain both electrolytic and film capacitors. Now, the de facto answer, anytime somebody says why, or somebody asks, why did they use low value electrolytics like 0.33 microfarads or 0.47 microfarads or even 0.22 microfarads? Why didn't they just put in a film capacitor? The de facto answer has always been because the electrolytics are physically smaller. Well, if that was the case, you wouldn't see those other caps that are film caps on the same board. They are a little bit bigger, but really not enough, that much bigger that it would make a difference where they couldn't fit them on the circuit board. So there has to be more to it than that, especially with a 0.22 or 0.33 microfarad at 50 volts. A film capacitor of that size would be very small, and it would fit in the general area that the electrolytic is fitting in. There has to be something more to it, and there has to be something different about the way an electrolytic capacitor works by having an electrolyte and a dielectric and everything that's chemical based. There has to be something about that that's advantageous to that part of the circuit. This is something that I don't know or understand, and it's something that I'm sure the folks that designed all this back in the 1970s understood very well. I think it was a thing they did on purpose, and I don't believe that it was something they did just to save a few shekels on the cost of the caps, or to make it be a little bit smaller, compact size. Those amps were designed back then with the audiophile in mind. A lot of these things, people were willing to spend large sums of money to buy them, quite frankly. And I mean, you look at the money that people spent, everyday people, not even just audiophiles, but people that wanted good sound in their house, they were willing to spend the money on it. I don't think they would have cheaped out on the capacitors for that. So if any of you have a different explanation other than because it was smaller and cheaper to manufacture those small electrolytics, please share it in the comments. I would love to know. I genuinely would. I've been thinking about it quite a bit. It fascinates me, and I'd like to know. Okay, this next little section, I'm going to call it the Emperor's New Capacitors. If any of you have read the story, The Emperor's New Clothes, you'll know what I'm talking about. If you haven't, just Google search it. It's a short story that only takes about 5 minutes to read, and it's kind of interesting. But, and I'm not going to get into that right now. What I am going to talk about is when I get a lot of comments about one type of capacitor versus another. Like, I like the Nichicon whatever it is series, or I like the Elna whatever it is series, or I believe that this real boutique version high-priced capacitor sounds better. That's always given me pause for concern. When you say that a capacitor sounds better, that it sounds more open, or a more warm, or a more full sound, whatever kind of description you put, that's a little bit concerning when you think about it. The purpose of an amplifier is to take a signal that is fed into it and increase its amplitude, and then be able to provide the amount of current that is required to maintain that amplitude into whatever load that it is feeding it into. In other words, what comes out should be the same as what goes in, except louder, right? That's called being transparent. Now, if an amplifier changes the sound in any way, then I would call that distortion. Now, some people say an amplifier sounds warm, or it sounds very open, or many different words that are used to describe the sound of an amplifier. But truth be told, anytime a signal changes from when it goes in to when it goes out, even if it changes for the better, it's distortion. You're distorting a signal. Now, when you think of a complex waveform, think of a song that you're listening to, and take any split moment in time of that song, whatever tone you're hearing a combination of multiple sounds. You're hearing the vocals, you're hearing the drums, you're hearing the guitars, you're hearing the keyboards, you're hearing whatever instruments are being played all at once, and they all combine to create what we call a complex waveform. Now, we know from our oscilloscopes, if we use FFT, which is fast Fourier transform, we can break down any complex waveform and define it as a series of sine waves at different amplitudes, right? A capacitor is a reactive device. Its purpose is to add a capacitive reactance to the signal that you're feeding it through. Now, the capacitor can do one of two things. It can either, the signal can pass through or pass by that capacitor and not be affected because of the frequency of the signal that's passing by it or passing through it, or it can induce some sort of a capacitive reactance to that signal, which will change the signal. Now, when you're looking at a complex waveform, if you take any one of those multiple sine waves that make up that complete waveform, and you change even the amplitude of that one particular frequency domain, you've just changed that tone totally. You've changed the complex waveform, and therefore you've distorted it. Now, to your ears, that might sound good, right? But you have still changed that waveform. So capacitors, in my mind, the best thing you could say about a capacitor is that I don't hear it, right? If a capacitor is in the audio path, the best compliment you could pay to it is that I don't notice those capacitors when they're in there. In theory, every single capacitor that you put in there, no matter which one it is, should sound the same. So when someone says they recapped an amplifier, they either said one thing. They either said one thing or the other. They're telling you either they took a capacitor that was distorting the audio and replaced it with one that is not distorting it, or two, they're saying they took a capacitor that was distorting the signal in one way and replaced it with a capacitor that distorted it in a more pleasing way, right? But those are the only two choices. It either changes the distortion or it removes the distortion from the capacitors that you're replacing it with, right? Right. So that's all I wanted to mention. Think about it. I was thinking about that. And I often think to myself when people say, I prefer the Elna, whatever it is, Elna Similac or whatever. No, Similac, I have a grandson. Similac is baby food. The Silmic or something like that, I don't know. You guys know which one it is. Or the Nichicon FW or the FGs or the K series. One sounds better than the other. I often wonder what that means. What am I really meaning by that? Am I changing the sound by changing that capacitor, or am I making the sound transparent? I don't know. All right, food for thought. Last but not least, I want to do a little experiment. what we're going to do is we're going to go back again to the 2285, the last video that I did. And when we were using the spectrum analyzer and we were kind of comparing the ratio of the fundamental frequency, in other words, we were feeding a 1 kilohertz tone into the receiver when we were testing it. And we were looking at that little bump of the second harmonic that was coming through this, of distortion. And I made the mention that it was about a 70 dB difference. The peak of, if I recall correctly from the video, the peak of the 1 kilohertz fundamental was kind of in between 2 gradicules, and if you counted down exactly about 70 or 7 gradicules from there, the second harmonic was sitting about between 2 gradicules as well. So if you measured it, it was very close to being right at minus 70 dB. And if you do the math, it turned out from an amplitude of the voltage, it was turning out that the harmonic was about 0.00316 of the fundamental as far as comparing the amplitude. That means that if we had 1 volt RMS of signal in the fundamental, then that means we would have 0.0036 volts or 3.16 millivolts of the second harmonic. So when you compare 1 volt to 3.1 millivolts, not a whole lot. So what I decided to do is I decided I was going to go on to Audacity, and we're going to do a little blind test. I'm going to create a fundamental tone that's an amplitude of 1. In other words, that'll be our standard. Then I'm going to create a second harmonic, which will be 2 kilohertz, and I'm going to intentionally make that 2 kilohertz tone at 3.16 millivolts, or 0.0316 of the amplitude of the fundamental harmonic. I'm then going to play it. I'm going to record it as a wave file, so an uncompressed wave file. And because it's only a 1 kilohertz and a 2 kilohertz tone, we don't need really super high-end audio file recording. You're listening to 2 tones. It's not much, and they're right in the middle of your hearing range. And what we're going to try to do is we're going to try to see if we can discern the difference between the fundamental and that little bit of what we're going to call harmonic distortion. That's going to represent 0.003% harmonic distortion. That's quite a small amount. I've heard people claim that they can hear it. I'll just give you a little spoiler alert. I did try listening to them at those 2 different amplitude levels, the 1 kilohertz tone and then the 2 kilohertz at the 0.00316. If I turned the volume up loud enough, I could hear the second harmonic. But if I had both of them on, I'll admit, it was ear-shattering how loud the fundamental was. I could not hear the harmonic. Now, I'm going to play this for you. What we're going to do first is I'm going to play a fundamental tone of just 1 kilohertz. And I'm going to play it at that 1.0 volume, okay? And you're going to adjust your volume control until it is a comfortable volume level for you. So we'll play that tone for maybe about 5 seconds, something like that, and it'll give you a chance to adjust your volume. Then I'm going to play the 2 kilohertz harmonic tone, and I'm going to play that at the 0.00316 of the amplitude of the fundamental. And here's the thing. You have 2 choices. You can leave the volume control alone, don't touch it, and try to find out if you can actually hear that first harmonic. Or you can turn the volume up until you can hear that harmonic. But I will warn you, turn your volume back down or this thing will rip your eardrums out. That 1 kilohertz tone is very annoying because it's right in the center there where we can hear. Then what I'm going to do, after we play the fundamental at full volume and the 2 kilohertz at that reduced volume, you know, to the 0.003, then I'm going to play 3 tones, one after the other. And some of those tones will have just the fundamental 1 kilohertz, and some of them will have the 1 kilohertz and the 2 kilohertz together. Your job is to tell me of 1, 2, and 3 which ones are the ones that have the harmonic distortion in them. Now I know this isn't a perfect distortion test, but this should be very easy because you're only listening for 2 tones. You're not listening for all kinds of other things that distortion can do in the real world. So if you have a really finely tuned ear, you should be able to tell me which one of those 3, or which ones of those 3, because I could have one of them have the distortion, or I could have 2 of them have the distortion. The only clue I'll give you is at least one of our 3 test tones will have the harmonic in it, and at least one will be a pure 1 kilohertz without the 2 kilohertz harmonic. So that's what we're going to do. So you're going to hear the fundamental, you're going to hear the harmonic, and then you're going to hear the 3 tones, 1, 2, 3. You tell me in the comments section, 1, 2, or 3 of those last 3 tones, which ones you think have the harmonic and which ones don't. Okay, that's your challenge. Are you ready? All right, I'm going to play them now. Okay, what do you think? Were you able to hear it? Were you even able, if you were one of the folks that did not adjust your volume after you listened to that first 1 kilohertz tone, were you able to hear the 2 kilohertz by not adjusting your volume? Or did you have to turn the volume up to be able to hear it? I think those who were wearing headphones had a much better chance of hearing it than those who were not. Those who were in a very quiet room with very good speakers may have had a better chance of hearing it, I don't know. But more importantly, were you able to hear of 1, 2, and 3, those last 3 that I played you, which ones of those had the distortion in them, or the harmonic, we'll call it? Let me know. All right, I'm going to come back later. I'm not going to tell you in this video. Maybe I will edit the description later on to tell you which ones were which, but I'm going to give you guys a chance for that. Or in the next video we post, I'll tell you what it was. So until then, I hope you had fun with this little short video, and I'm going to wish you all peace, joy, happiness, and good health in your lives. We'll be seeing you again real soon, and just making some decisions what project I want to put up on the bench next, and what kind of time I'm going to have to do it, because things are very busy right now, and I've been out of town, in and out, and so forth. So we'll try to get some bench time in if we can. All right, take care, everybody. Bye-bye.